In this example, we have to calculate the second moment of area for our C section about a horizontal axis and about a vertical axis that goes through the centre or the centroid for the given shape. Before we work out Ixx and Iyy, we have to calculate the position of the centroid, which is denoted by X bar and Y bar. For our shape, we're going to divide it up into a number of rectangles. This can be achieved by splitting the shape with two horizontal lines into three rectangles, labeling them 1, 2, and 3. For each of the rectangles, going to position the center for each of the rectangles. And I want to note down the position of the center of each of the rectangles from one common reference point, which will be the lower left hand corner of our section. Our reference point given in green is like the origin on a graph with coordinates 0, 0. Relative to the reference point, I want to write down the coordinates of the center for the first rectangle, second rectangle, and third rectangle. Doing that to the side, the center for the first rectangle will be 80 millimeters across and up a total distance of 125 millimeters. For the second rectangle, its center is given by 5 millimeters across and up 70. And for the third rectangle, its center is given by 110 millimeters across and up 10. Underneath each of the set of coordinates, I'm going to write in X and Y, but for the first set, I'm going to write in X1 and Y1 because they relate to the first rectangle. Underneath the second pair, I'm going to write in X2 and Y2. They relate to the second rectangle. And for the third set, X3 and Y3. Now using the equation for X bar, which is sigma AX over sigma A. In this case, we have three rectangles. So we take the area of the rectangle, multiply the distance to its center, area 1 times x1, plus area 2 times x2, plus area 3 times x3, and we divide that by the total cross-sectional area for the section, which is given by area 1 plus area 2 plus area 3. In this case, area 1 is 160 mils by 10, and the x1 dimension given at the top is a value of 80. For the second rectangle, it's 10 across by 100 deep. X2 value 5, plus then area 3, which will be 220 by 200. X3 dimension is 110. Divide that by the total cross-sectional area, which is 160 by 10 plus 10 times 100 plus 220 times 20. Working that through, six one seven 000 divided by 7,000, and that gives you an X bar value of 88.1 millimeters. Repeating the same process, but now for y bar. The equation is sigma AY over sigma A, and in detail that will be area 1 times the distance y1 plus area 2 times distance y2 plus area 3 times distance y3, all divided by this same cross-sectional area, which is the three individual shapes added together. Filling in the values we have, area 1 is 160 by 10. The y1 dimension from the top is a value of 125. Area 2, 10 by 100. The y2 dimension is a value of 70. Area 3, 220 by 20 by y3, which is a value of 10. That gets divided by the total cross-sectional area, 160 by 10 for the first rectangle, 10 by 100 for the second, plus then 220 by 20 for the last rectangle, and that would give us 314,000 divided by 7,000, giving us a value of y bar to be 44.9 millimeters. For the next part of calculating the second moment of area, we're going to use our standard table. In this, we have a number of columns: B, D, BD cubed over 12, A, Y, Y bar, value for H, AH squared, BD cubed over 12 plus AH squared. This will take into account the parallel axis theorem for working out the second moment of area of a shape about another parallel axis. To fill in this shape, we're going to use the first three rows because we have three rectangles, and using the B and D dimensions, remembering that for a rectangle, B will be the horizontal dimension and D will be the vertical dimension. So reviewing the section we actually have, our first rectangle will have a B dimension of 160, the D will be 10. For the second, it will be B will be 10, the D will be 100, and for the third, B will be 220 and D will be 20. We can fill these values in. $160 and 10, 10 and 100, 220 and 20. Based on the B and D values, we can calculate the second moment of area for a rectangle about its own centre. It's given by the equation BD cubed over 12. Using each of the three pairs of values, we can calculate and fill in the values in this column. First one, 13,333.3. Next one is 83,333.3. And the last one, 146,666.7. The next column relates to the area, which is simply the B and D dimensions multiplied together. Filling that in, we get 1600, 1000, and 4,400. The next value, or next column, is a y. So going back up to our original diagram and the coordinates for the center for each of the rectangles, we have a value for y1, y2, and y3. y1 is a value of 125, y2 is a value of 70, and y3 is a value of 10. These are the three values that fill in under the y column. 125, 70, and 10. Y bar, as you can see, we have y bar calculated, 44.9 for each of the three rows. H takes into account the parallel axis theorem and is given by y minus y bar. Using the values for y and y bar in each row, 125 minus 44.9 gives you 80.1, then 25.1, then minus 34.9. To apply the parallel axis theorem component, parallel axis theorem states that the second moment of area of a shape about another parallel axis is the second moment of area of the shape about its own axis plus AH squared. So for that, we need to calculate AH squared, remembering that it is the area multiplied by H squared, and it's only the H value that gets squared. And when you have negative values for H, as we do in the bottom, squaring a negative number gives you a positive number. Filling in the values, taking the area for the first row of 1600 and multiplying it by 80.1 squared, you get 10,265,616. For the second row values, the 100 or 1000 it should be for the area, times 630,000, and for the last set, where the area is 4,400 multiplied by minus 34.9 squared, Squaring a negative number gives you a positive number and gives you a value of 5,359,244. Then for the last column, we take the AH squared value and add it to the BD cubed value. Doing that, we get for the first row 10,278,949.3. For the same two corresponding values in the second row, we get 1,463,333.3. And for the last row, adding the two corresponding values together, and we get 5,505,910.7. Then to calculate the second motive area for our shape about a horizontal axis through the centroid, we would add together the values we have in the last column. So adding our three values together, we get a total of 17,248,193.3. All the dimensions are given in millimeters, so therefore our units will be millimeters to the 4, or in condensed form 17.248 times 10 to the 6 millimeters to the power 4. Now to calculate the second motive area about a vertical axis, IYY, we use a slightly different form of the table. In the first instance, it looks very similar with D and B values for the dimensions. For the second motive area about a vertical axis, we now use dB cubed over 12. Area, again, will be B times D. And now we're going to use X bar. Again, going to use the parallel axis theorem. Have to work out the offset between the axes. H, AH squared, and finally then D, B cubed over 12 plus AH squared. Now, looking back at our original diagram, we're going to fill in the B and D values, 160 and 10, 10 and 100, 220 and 20. Now using the formula dB cubed with our B and D values, we calculate dB cubed over 12 for each row, and in the first one we get 3,413,333.3. For the second row we get 8,333.3, and for the last row we get 17,746,000 666.7. Now, using for the area column, multiplying B and D together. In the first row, we get 1600, 1000, 4400. In this calculation for IYY, we're going to use the X values. So back up to our diagram, and this time round the X values we use are going to be the X1 value, the X2 and the X3 values. They will go into the row corresponding to the number for the shape. So 80, 5 and 110. X bar, if we go back up, we'll see that we calculated a value of 88.1 for X bar. Fill that into this column. And then we're going to calculate H, which is the offset between X and X bar. So it's X minus X bar for H. Work out the differences. Minus 8.1 minus 83.1, 21.9. Now, with applying the parallel axis theorem, we need to calculate AH squared, remembering it's the area times H squared. It's only the H component getting squared. Squaring a negative H value gives you a positive value. So for the first row, take the minus 8.1, square it, multiply it by the corresponding area, which is 1600, and we get 104,976. For the second row, minus 83.1 squared times the area of 1000 gives you 6,905,610. And for the last row, 21.9 times 4,400 gives you 2,110,284. Now, when we're applying the parallel axis theorem, we take that component of AH squared and add it to BD cubed. And we place that total into the last column, giving us 3,518,309.3. Then with the values in the second row, adding these two together, we get 6,913,943.3. Then for the last row, adding these two together, we get 19,289,203.3. Then to work out the overall second moment of area, we add up the values in that last column, taking our three values highlighted in green Adding them together, we get a total of second moment area for Iyy of 30,289,203.3. Dimensions given in millimeters, so for the units for second moment area will be millimeters to the power 4, or writing it in a shortened form, second moment area will be 30.289 times 10 to the 6 millimeters to the 4.